The next reaction I would like to mention is the electrophilic substitution, which is by far the most important reaction in aromatic chemistry. The mechanism usually follows a two-step sequence, where the first reaction is the addition of electrophile, and your aromatic or heteroaromatic is the nucleophile, using the electrons from the pi system to attack electrophile. After that, this will lead to the formation of the charged intermediate here, and this step is breaking the aromatic system. Therefore, the reaction is slow, and it is usually the rate determining step. Now, the second step is the regaining of aromatic system, and this can be achieved by elimination reaction. So this is usually and the thing that is usually eliminated is the proton. But however, there are some other groups that can be eliminated as well as a positive charge. So in this step, the proton is removed, you regain the aromatic system, and you can see that starting from hydrogen, now you have replaced it by electrophile. Therefore, it is called substitution reaction. And in most circumstances, this step is reversible, and the product is determined by kinetic control. If you can have more than one product, the product that is gives the product has the lowest EA and the reaction is fastest would be the major product in this reaction. There are two types of heterocycles that we will focus in this course, which is 5-membered and 6-membered ring. So if you have a look at the 6-membered ring first, this species usually contains some kind of basic nitrogen species. For example, pyridine has a nitrogen that contains lone pair that can interact with electrophile in the reaction mixtures. For example, protons in nitrating mixture or aluminum chloride in Friedel-Crafts combination. And this interaction between nitrogen and electrophile is faster than any carbon substitution. Therefore, when the nitrogen reacts with this electrophile, it will create the positive charged salt like pyridinium ion, and this will even decrease the nucleophilicity of this kind of reaction in the 6-membered ring heterocycles. So before we look at the pyridine, we can see the difference between electrophilic substitution of benzene and electrophilic substitution of NNN trimethyl anilium cation, which is the benzene that has the quaternary ammonium salt as a substituent. And we know that this positive charge can pull away electrons from the aromatic systems, and therefore the attack of electrons from aromatic system to electrophile is worse, and this is 10 to 8 times slower than that of benzene. If you compare pyridine with benzene, the nitrogen already have some electronegativities and pull away electrons from the aromatic system. And doing electrophilic substitution on the pyridine itself is 10 to the 7 times slower. However, as we mentioned that in the electrophilic substitution, you have some electrophilic species. For example, if you want to do nitration, you have nitric acid and sulfuric acid, and under these conditions, the pyridine is converted into pyridinium salt. And because you now have the positive charge, it will even it pulls the electron from the aromatic system even more, and therefore it is even worse than the pyridine itself, and therefore there is no reaction for the nitration using this condition. So from the reason that I mentioned in the previous slide, the heterocycles with a pyridine type nitrogen do not easily undergo electrophilic substitution, but there are some exceptions. So if your molecule have another fused benzene ring, that means that benzene ring can act as a nucleophile. So if you look at this quinoline, you have the pyridine that is fused to benzene ring, and when you do the nitration, first definitely it will be protonated into the quinoleum salt, and now this half of the system is now not nucleophilic anymore. However, you still have the left half, which is the benzene, which gets electron pulled away a little bit, well, actually quite a lot, by the salt, but still it is more nucleophilic than the right half. So the reaction will take place on the left ring instead. And the reaction reacts at the fifth position because the positive charge can delocalize between two positions. If you react at another position, this will lead to no stabilization from the conjugation. And at the end, you will get the 5-nitro quinoline as the final product. However, the reaction is 10 to the 10th time slower than the simple naphthalene. Another exception is when your ring system has some substituents that can activate the ring. So the term activation means that it is the electron donating groups that can release electrons into the ring either by inductive effects or mesomeric effect. By the way, make sure that you understand these two terms. Inductive means that it gives electron through sigma bonds, and mesomeric means that it gives electrons through pi conjugation system. Okay, and when electron is given into the ring, that means the ring can has more electron density and can give electrons to the electrophile faster than usual. If you take a look at the example 4-pyridone, which is the kind of like a pyridine that has a ketone group at the 4 position. If you look at this molecule, you may think that, okay, ketone is the electron withdrawing groups, but actually, if you perform nitration of 4-pyridone, what is going to happen first is that the oxygen gets protonated. So you can draw electron from the lone pair of nitrogen here and from this double bond to here, and then the electron is given to the proton at the oxygen, and you form the hydroxypyridinium species, which, if you look at the oxygen, it has some lone pair that can delocalize into the ring and activates the auto position to attack the nitrating agent. Therefore, you can react the 4-pyridone at the 3 position. And after deprotonation, this gives the substituents at the 3 position of the 4-pyridone. So the position at which the electrophile will attack will depend primarily on the orthopara director, I mean the OH, for example, in the pyridone. And for example, this will lead to the electrophilic attacks at the orthopara to that group. For this species, it will direct to the ortho and para and ortho positions here. Another exception is quite counterintuitive, where when you have more electron withdrawing groups on the pyridine, for example, this 2,6-dichloropyridine, you would expect this to be even less reactive towards electrophilic substitution than pyridine. However, if you look at the equilibriums between the neutral species and protonated species, you can see that if you compare to the pyridine, it will completely protonate into the protonated species. But when you have some electrophilic species here, you can have some of them that is still in the neutral form, so that this neutral form can be the one that reacts with the nitrating agents and leading to the formation of the meta-substituted nitro groups here. But when you get protonation, the reaction will not occur. Okay, but anyway, when the reaction proceeds, some of this some of the protonated species can equilibrate back, and it will drive the reaction towards the formation of the product. So this leads to this the rule of which the pyridine with a pKa(H) higher than 1 will nitrate as a cation, because under acidic conditions this will get protonated, and this will be even less nucleophilic, and sometimes it never nitrates at all. For the weakly basic pyridines with pKa(H) less than minus 2.5, some of the neutral species, the free base, can be the species that gets nitrate, and now you have some chance of nitrating. However, if your pyridine has some strong electron withdrawing groups, or if you have some heterocycles that has additional heteroatoms like in diacenes, these species are so deactivated that the electrophilic substitution will never take place. Anyway, I would like to summarize that for the 6-membered ring heterocycles, electrophilic substitution is not good for them, and this is not the usual reaction that we will use for these kind of heterocycles. On the other hand, for the 5-membered heterocycles, now the electrophilic substitution is one of the major reaction in this kind of molecule, because these molecules have electron-rich heterocycles and can react well with electrophiles. For example, pyrrole, thiophenes, and furan can undergo a range of electrophilic substitutions very easily, and the reaction can occur at either type of ring positions. That means it can react at alpha or beta, but it is preferred to attack adjacent to heteroatoms. So the reaction at the 2 position is the major product. And the reaction follows the same mechanism. However, you can use the lone pair of heteroatoms to feed into the ring and then attacking at the 2 position. And when you eliminate the proton, it can rearomatize and makes the nitrogen neutral again. So as we mentioned, that the substitution is facilitated by electron release from the heteroatoms. Therefore, we can think of these heterocycles as electron-rich heterocycles and react very well with electrophiles. If you compare the electrophilic substitution between pyrrole, furan, or thiophenes, you can see that the rate of electrophilic substitution of pyrrole is much faster than that of furan or thiophene. And this is because if you compare between nitrogen and oxygen, the nitrogen has less En than oxygen, and therefore the lone pair of nitrogen is much more available to give to electrophile than oxygen. This is similar to if you compare the basicity between amines and alcohols and stuff like that. And if you compare between furan and thiophene, we know that thiophene is much more aromatic-like, as we mentioned in the first lecture, that it is much more stable than furan, and therefore breaking aromatic system of thiophene is harder than breaking the furan aromatic system, and therefore it makes the reaction slightly slower than that of furan. If you look at some of these examples, when you have a molecule that have both furan and thiophene, you can see that acetylation will occur at the furan part, and if you join the thiophenes and pyrrole to each other, definitely the reaction will occur at the pyrrole part. In terms of regioselectivity, you can see that the reaction can occur at both alpha and beta positions, but the reaction prefers to react at the alpha position as the major product. So you can see for pyrrole, the difference is not that much, but for furans and thiophenes, the alpha position is the major species. But if you want to react at the beta position, you can do this by introducing a bulky group at the nitrogen, and this will block the alpha attack and leading to the attack at the beta position as the major product. And after the reaction finish, you can choose to remove this bulky group out at the end as well. This is possible as well. For the reason why the reaction prefer to react at the alpha over the beta position will be mentioned in other lectures. Okay. If you look at indoles, which is a pyrrole fused with benzene ring, it is only slightly less reactive than pyrrole, but the major difference is that the regioselectivities of indole will prefer to react with electrophile at the beta positions. So if you look at this Wills-Mayer combination, by the way, these two reagents can react with each other by nucleophilic addition of this oxygen to the carbon here, kicking out the leaving group, and then forming N double bond Ne2 plus. And now this part is a leaving group. So your chloride can now attack. So this can attack here, kicking electron to here, and kick back and kick out this, removing carbon dioxide as a gas, driving the reactions. And then you have the Wills-Mayer reagent, the real active species, which is like a super strong acid chloride. This is a very strong electrophile that can react with many types of nucleophile. For example, this heterocycles can use the carbon to attack here and kicking out the chloride. And then you form the iminium salt, and after the hydrolysis, the workup step, the iminium salt can be hydrolyzed to form the ketone here. Okay. So for pyrrole, the reaction occurs at the alpha position with the rate 3 times more than the indole. But for indole, you can see that the major product is the beta position. The regioselectivity is like 1 to 2600. But however, these two species are much more reactive than that of benzene, like 1 billion times more reactive, something like that. The reason why reactions of indole occur as beta position, I will mention again in the next lecture. Okay. For heterocycles that have more than one heteroatoms, for example 1,2 or 1,3 azoles, you have additional nitrogens of the pyridine type, and we know that this type of nitrogen is electron withdrawing and then make the electrophilic substitution slower than the usual the parent ring. So it reduced the reactivity, and this is due to the inductive and mesomeric withdrawal effect, as well as the addition of electrophilic species. So if you have the protons, this can get protonated and then even reduce the reactivity of the ring system. Okay, more detailed explanation of this kind of reactivities will be discussed in lecture 6.